Well, hello everyone. This is the third day of the conference, so I will keep the informal introduction short. I'll just briefly introduce myself and then we'll dive right into the talk. So who am I? My name is Sebastiaan. In my day job, I work for the Ordina Pythoneers, which is a company in the Netherlands. And I'm also one of their codesmiths, which means that I get to do things like this, go places, do innovation, outreach, talk with people, but also a little bit of education. So I'm really happy with that. In my spare time, I'm one of the organizers of EuroPython. I'm one of the volunteers for EuroPython, which is a really cool conference later this year. So definitely check it out. It's in person in Dublin, but there are also remote options. So it's fit for everyone. And I'm also one of the 3 owners of Python Discord, which is a large online Python community. If you haven't checked it out, you should definitely check it out. Well, that's it for me. Let's start with my talk. So what are we going to do today? Well, we're going to make a journey through CPython, or the Python internals. And I want to take you on a journey from the source code to the execution on the other side, or what I would like to call magic, because I think it's really magical that you write something and the computer actually does something. We'll see a lot of parts. In between, we're going to talk about tokens, grammar, the peg parser, abstract syntax trees, and all the other stuff listed there. And the excuse that I've thought up for that is that we're going to implement a new operator for Python, a pipe operator. Now, obviously, there's another big feature thing in my talk, and that's due to time constraints, and that's blatant omissions and gross oversimplifications. But luckily, there are great resources out there for if you want to know more. So first of all, there's the Python Developers Guide. You can access it on devguide.python.org. And it has a treasure trove of information about contributing to Python, the Python internals, and it also lists great other resources. And then next to it, you see Anthony Shaw's book, published with Real Python, CPython internals. You should definitely check that one out as well. In that book, they use Python 3.9, so that's why I've picked Python 3.9 for my talk as well, just to be fully compatible with the book. So what are we going to do? We're going to start with the source code, and then we're going to make the journey all the way to the magic, to the execution of the source code. And if you want to read along with the source code itself, the things that I've implemented, you can find it on my GitHub page. There's a project called Python in it, because we're going to implement a pipe operator. And there you can check out also the slides of the talk. They're in there as well, in the presentation folder. So, what kind of operator are we going to add? Well, we're going to implement a new binary operator, an operator that takes 2 values and does something with it. And it's a pipe operator. So let's say that you have a very simple function. It takes 1 argument and it returns a single thing. With this pipe argument, you could write your function call like this. So you have an argument on the left-hand side of the operator, then you have the operator, and then you have the function on the right-hand side. And it's basically just like passing the argument to the function, and then you'll get a result. And the really cool thing here is that at the end, we'll be able to chain it as well. So in this case, we start with the 1, we double it, and we double it. We end up with 4, which is equivalent to the 2 nested function calls you see over there. Now, obviously, this is not an actual operator in Python, and I don't think it will ever be. There's been a lot of discussion about this, a lot of good reasons not to implement it, but it's a nice toy example for the talk. And also, I'm going to keep the implementation simple. The source code is available if you want to play around with it, make it more complex, feel free to. It's a nice experimentation, but I'm going to keep it simple. And that's what we're going to do. So, let's move on to the first part. And the goal of the first part here is to take your raw source code and turn it into something called an abstract syntax tree, which is the graph you see on the right-hand side of the slide. This is just a representation, in this case, of an entire module in Python that just consists of this single line. And that's what Python needs to do first. Now, let's first zoom in on the source code. We humans, we are really great at chunking things. So we will immediately see that we have a number, we have an operator, we have a name. But for Python, when it first starts out, these are just individual characters. So the first step that Python takes is to turn this into tokens, the smallest parts in your source code that you cannot divide any further without losing their integrity. So the tokenizer will recognize the first part as a number token and the last part as a name token, but the new operator, it doesn't exist yet. So it doesn't quite know what to do with that. And in fact, there are two separate tokens there, a vertical bar and a greater than. But we need to turn that into a single token. Well, is that difficult? Well, not really. Because in the Python source code, there's a grammar folder and there's a tokens file in there. And this is basically just mapping the name of the token to the character sequence of the token. So you can see a few here. At equal is the character sequence of an at and an equal sign. And we're just going to add a new entry to this, the v-bar greater, map it to the characters. And basically, this is enough to specify the token. There's just one small catch, and this is something that we'll see a lot today. This is just a configuration file for the tokenizer. The tokenizer itself will not read from this file whenever it's parsing your code. So we have to regenerate the tokenizer, and there's a very simple command for that. If you use make on Linux or Mac, it's just make regen token, and it will then remake the tokenizer, including the new token, so that it's aware of our new token. On Windows, you can use the build.bat file, --regen. This regenerates a lot more than just a tokenizer, but it will also regenerate your tokenizer. And just like that, we now have a new token in Python. There's one small problem. It's not actually part of any grammar rule yet. So there's no syntax in Python that actually uses this token. So if you try to use it, you will still get a syntax error. So we have to include this token in a new grammar rule of Python. So that's the second step that we're going to do here. We now have the tokenizer has run. We have a stream of tokens. Now we need to make a grammar rule. And in Python 3.9, with the new peg parser, that peg parser will use that grammar and immediately construct that abstract syntax tree that we saw earlier. In the past, there used to be an intermediate step with a concrete syntax tree. With the new peg parser, we don't need that anymore. So it can immediately translate your piece of Python code in such a nice tree structure, but we do also need to add support for the new operator in the AST, in the abstract syntax tree. So that's what we're going to do now. And to specify that new grammar rule in Python, we need to use the syntax of the parsing expression grammar, or PEG, which is the new parser that was added in Python 3.9. So let's first look a little bit about that grammar. And I'm going to very much simplify it. There's a very detailed explanation in the dev guide, which has all the options in there. But we're just going to look at what we need. And these are two very simple grammar rules. They're simplified. They're not entirely valid. But it's just what we need to implement our own later on. And I've color-coded it here so that you can see that the bottom rule, the atom rule, is actually contained within the sum rule here. So how does this work? If you look at the sum rule, it has two vertical bars with which it starts, and that specifies the two options for this rule which we can parse. So if you look at the top, we can parse atom plus atom, and if that fails, the parser will move on, and it will try to parse an atom on its own. And that's how the parser gets from the sum rule to the atom rule. So let's see that in action. So here we have a 1, a very simple piece of syntax, and obviously it won't match the one with the plus in it because there's no plus here, so that fails. It moves on to the next rule of sum, which is just an atom. An atom is defined as just a number token, so this will parse as an atom, and this works just as well. Now, we can now also parse this piece of syntax, because obviously it has an atom, a plus sign, and then another atom. So we can actually parse this just fine. It will match the first rule in the sum, and it will work. But now let's take a look at this piece of grammar and think about it. Can we match this one? Well, if you think about it, it will first try to match the atom plus atom. It will succeed. It will consume those characters. And what we're left with now, assuming that there's a rule higher up that allows for more sum patterns in a row, we've ended up with +3, and there's nothing in my two rules that's able to match +3. So what should we do? Should we add a specific rule for 2 plus signs, and then maybe for 3 plus signs, and 4 and 5? Add a lot of rules? Well, that's not really convenient, but luckily we can change the first sum rule. What we can do is we can make it recursive. So now the first sum rule actually includes the rule itself. And this is really convenient, because now we can match the first part, but we can also match the second part, because a sum can start with the pattern itself. And obviously, due to recursion, we can now have an arbitrary number of operators in a row, which is really convenient, and also what we want to do with our pipe rule, because we want to make pipelines arbitrarily long. So let's implement the logic for our pipe rule. For that, we'll need to open the grammar python.gram file. There are a lot of rules in there. I've just picked a place in the middle where it's easy to insert a rule. This is not the optimal place. You'll see that if you use this Python version, that you'll have to wrap, say, a lambda in parentheses, which is not ideal. Challenge for you, improve on that. But this is a place where I only have to make a few changes to make it work. So I'm just going to make some space here, and I'm going to enter a new pipe rule. And the pipe tool is an expression type, that's what it returns. Don't worry about that for now. But what is important here is that we have this recursive relationship. So it includes itself, and now we're able to parse arbitrarily long pipelines. Well, that's fun, but we're not quite done. The problem is that this pipe rule isn't yet referenced by any other rules. So if you look at the shift expression at the top, it only references the sum, so it will jump over our rule. So I have to modify that as well. I just insert the pipe rule there, and now our new pipe rule is between the shift expression rule and the sum rule, and now it's part of the grammar that will be parsed. Cool. So now we can actually parse the thing that's on the left. But we're not quite there yet. Another thing that we need to do is we need to tell the parser how to turn what it has just parsed into that AST node on the side. And this is the AST, the abstract syntax tree representation of a binary operator. We have a lot of those in Python, plus, minus, left shift, right shift, and so on. And all of them have a part that's on the left of the operator, it has an operator, and it has a part that's on the right. So in this case, we can just use the generic bin-up AST node, and what we're going to do is we're going to specify that we have this call pipe operator in the middle. So this is our goal. So how can we do that? Is it really difficult? Well, actually it's not. There's such a thing as grammar actions in the new grammar, and we can see one right here with the sum rule. This is here. You can see curly braces, and between the curly braces there's a grammar action, and this is just a function in C. And this function in C is able to construct for us such a bin-up AST node. And what it needs in terms of information is the left-hand side, the right-hand side, and the operator. And there are a few extra bits which we are not going to worry about, things like the column number, line number, things like that. So as you can see in the sum, there's a little bit extra. There are two names, A and B. They are actually assigned to whatever is to the left of the plus sign is the A is sum, and to the right of the plus sign, B is term, is whatever's on the right. And that way we can pass it into that function, and that function knows what to do. We also pass in the operator itself here. We know that this is an add rule because it matches the plus, so we can specify the operator that we want, and now the grammar knows how to construct this node for an add operator. So let's just copy it to our pipe expression. We now also need to assign the A to the pipe and the B to the right-hand side, pass that in, and all we have to do here is specify that we have a new operator, a different kind of operator. Well, that sounds really easy, but there's still a problem, because this AST node doesn't exist yet. This is a new operator, Python doesn't know it, the abstract syntax tree doesn't have support for it, so we'll have to create that one. Is that difficult? No, once again, there's a configuration file, and you can find it in parser/python.asdl, abstract syntax description language, and this is just a specification file that specifies all of the AST nodes that are available in Python. And as you can see here, we have a list of operators, and this will be automatically turned into a C enumeration for us. And here we see the add operator to the left. And the only thing that we have to do is we have to add our call pipe operator to the end. And then when we regenerate Python's AST, abstract syntax tree, it will now include support for the operator. The call pipe will be added as a new enumeration value to the operator enumeration. And on Windows, the commands are there, but they're also in the dev guide. I'm not going to repeat them every time. So now we have support in the AST. We've implemented the grammar rule, and now we can actually regenerate the entire parser to include the new grammar and the new AST. And after this, if you then run Python, you can actually ask the AST to parse the expression that we have, and you'll find that it correctly creates a bin-up node and that it has a call pipe object AST node in the middle. So this is quite fun. And now we're actually done with the first part. We can take the source code, just characters, and turn it into an abstract syntax tree. Well, that's nice and all, but we're not quite there yet, because what is an abstract syntax tree? It doesn't do anything yet. So now we have to take that abstract syntax tree and turn it into something that we can actually execute, and that is the job of the compiler here. And what the compiler does, the compiler will take the abstract syntax tree and turn it into something called bytecode. And bytecode is actually then executed by the evaluation loop, and that is where things actually happen. So we have to add support to the compiler for our new operator. That isn't that... oh, I forgot about the slide. So I think I already said this. We have to create a new operation code in the bytecode for our operator. And that's because the bytecode is just a long list of instructions for the evaluation loop. And each thing that Python can do, actually execute, has its own opcode. So they're there for binary add, binary subtract, store name, retrieve name. And our new operation also needs such an opcode. So let's make one. Is that difficult? Again, no, it's not, but you have to know it. There's another file in lib/opcode.py. This is a Python file. And this just defines all the opcodes that we have. And now remember, an opcode doesn't do anything yet. It's just like an instruction. So it maps a name to a unique number or byte, but we think in numbers. And the only thing that we have to do is I have to add one line here. I name it something, binary pipe call. This is the name of the instruction. And it gets the new opcode integer of 90. And now whenever the evaluation loop gets 90, it knows that it has to perform this operation. It doesn't support it yet, but it knows that it will have to do that. Now I have to insert it a little bit up in the file, and since most of the codes are sequential, we also have to update all the codes that come after it. It's a bit of a hassle. Now we can regenerate all the opcodes, and just like that, we have a new instruction for our bytecode. So that's not really that difficult. There are just a lot of steps to remember. There's still one problem. The compiler will not actually know when to write that instruction into the bytecode. So let's do that. So in the compiler, there are various functions that get called, that get called whenever it needs to compile a certain type of node. And in this case, this function will eventually get called when it needs to compile an expression. And this is just one big switch case statement with all the AST node kinds that it has. So we'll have to implement something for the binary operation kind, because this is the kind of AST node that we had, and now we need to add support for it. So what will the compiler do? It will first write the instructions to evaluate the left-hand side of the operator. And this will be important later. To actually perform the operations, we need both values, to the left and to the right of the operator. So it will first write, make sure that the instructions are written to evaluate the left-hand side of the operator, then the right-hand side. We need both values. And then it will write an instruction to actually perform the operation. Now, it's a little bit hidden here, which instruction gets written, but it's actually in this bin-up function, and we can just check it out, that bin-up function. It's another switch case statement, and it just has as cases all of the binary operator bin-up operators, all of the things that are in the AST. Here's the add we saw earlier. It will then issue a binary add instruction. So we will have to add one for our new operation code, call pipe, and we will issue the new opcode that we have, binary pipe call. So now whenever the compiler sees such an AST node with the operator being the call pipe, it knows that it needs to write this instruction. There's one other thing that we need to do in this file. It's the stack effect. It has to do with the value stack. I'm not going to explain that to you, but if you add it with all the other binary operators, it will just work because we're going to remove one value from the stack later on. So that's cool. Now we can transform our source code all the way into bytecode in a list of instructions that the evaluation loop can actually execute. But the evaluation loop still doesn't know what to do here. So we have to add something to the evaluation loop. And the evaluation loop is really like Python's main loop. This is the thing that will process all the instructions. And it's a huge loop with a lot of switch cases, and it has a case for each bytecode instruction that it can have. So for instance, here I have the target, the case target for the binary subtract. This is within the evaluation loop. So what happens is as soon as the evaluation loop encounters the binary subtract, it will start executing this piece of C code over here. And this is what actually executes the subtraction. So for the subtraction, we need to have the right-hand side value and the left-hand side value because we want to subtract the right-hand side from the left side. So how do we get those values here? Well, this goes back to the order of the compiler that we saw earlier, because if you have an expression like this, 4 minus 3, the compiler will first write the instructions to evaluate the right-hand side, the left-hand side of the operator. And then it will eventually get that value, and it needs to keep track of it, because it isn't done with it yet. So it puts it on something called the value stack, so that the value is available for later instructions to use. Then it will parse the right-hand side, and again it will put it on the value stack, and then importantly it will put it on top of the left-hand side. So the right-hand side is the top value in our stack. And if we now look at the code that we have here, you see that the first instruction here, right, is a pop, which is a CPython macro, and it will just pop the last value of this stack, so that value will go there, and write will now point to the 3 object in memory. Then we have a top instruction. This is a little bit different. It doesn't pop a value, but it just looks at the value, but it means that left now points to the 4. And now we can call a special C API function, PyNumberSubtract. It passes in the left and the right values, and now it gets a result, which is the 1. It will then decrease the references of right and left because we're done with it. I'm not going to talk about ref counting here, but that's what it will do. And finally, there's a set top instruction, and what this will do is it will replace the current last value on the value stack, the 4, with whatever's in here. So it will now put the result back on the value stack to be processed by further operations. Now, this is very similar to what we want to do with our instruction, the binary pipe call. So I just copy the code, change the target to our instruction. Well, we still need the values, so we can leave the pop and the top, but I do have to change this function. We don't want to subtract, we want to call a function. Well, there's a special C API function for that. It's called PyObjectCall1arg. This one is new in Python 3.9, and it will call whatever here with this sole argument. So if you look at our pipe operator, it will call the double function with the value 10, and just like that, we have the result of the operation. And then it will decrease the reference counts, set the result back onto the value stack. There's some error handling here, and this dispatch just means we're done with this opcode. Please, evaluation loop, continue with the next operation code. And if we've done this, we've went all the way from the AST to the magic. We can now actually execute whatever it's in an abstract syntax tree, and that also means that we've now completed the journey from source code to magic. So, and with that, The only thing left to do is to compile it, specify our function, and just try out our new operator. And as you can see, it works. So, and that's it. You've seen a lot of CPython internals in a short time. I was hoping to give you an overview of the entire process, not a detailed thing. Source code is available here. And one final tip, if you do go play around with it, you get odd errors after compiling and compiling and compiling, it might be wise to use the clean commands just to clean up all the intermediate files that might still contain bugs from earlier versions. Right, before we go, check out EuroPython. There's a URL here. It will happen in July in Dublin and remote. Do participate, it's going to be awesome. And finally, this was it. You can get in touch with me there if you like. Thank you very much.
All right, thank you for your talk. We'll go right to questions. Was it really necessary to add a new opcode, given that there are already opcodes for function calls?
Was it really necessary? So I was playing around earlier with just using the opcodes for function calls, but I really wanted to show you this process. So this is more like a nice toy example, and I wanted to show you how to add such a new opcode. So that's why I did not opt to use the existing opcodes for calling functions. So it's more for the example than anything else. This is not an actual implementation. It's just a toy example.
All right. Does the grammar parser parse line from right to left or left to right?
Ooh, that's a really interesting question. That's defined by how you then handle the grammar and the AST. But that's a really difficult subject, and I'm probably not the best one to explain that. So I'm going to hop out of that question, but I can discuss it later in the chat or anything. But that's where things get really difficult.
Okay.
At least for me.
How does one specify the order of binary operations, for example, multiplication before summation?
What you will see in the grammar file is that it will actually have chunks of various grammar rules. And you should check that out, and then you'll see that it first has the sum rule, and then below it, it will have the rules for multiplication. And that's how it embeds those rules in each other. Just play around with switching those around, and you'll see an effect in what's going to happen.
What are some scenarios where you would be programming on this level?
Sorry, what are?
What are some scenarios where you would use this?
Well, for one, the biggest scenario I can think of is either that you want to contribute to CPython, or maybe you want to understand CPython to write a C extension to make something really quick or fast. Or for me, it's just to understand Python better, because I hope that makes me a better Python programmer. I really like to understand what Python is doing, so that I can reason about it a bit more clearly in my mind. I don't actually do this a lot in real life. I might want to try contributing to CPython in the future myself. That would be awesome. It's an awesome open source project, but I'm not sure. So I think those are the main scenarios.
Why do we not insert the opcode at the end of the file? Then we would not have to change all subsequent opcodes.
Well, that's a really interesting question. So the order in which you define all the grammar rules also defines what kind of expressions you can have nested within all the other expressions and what the order of operations is. So by defining it here, I already have the problem that the grammar rule specification for a lambda definition is higher up. So I cannot use a lambda expression within my pipe operator, which is a bit inconvenient because with functions you might want to use lambdas. So now you have to wrap those in parentheses. So it really does make a difference where you add those rules. And as a challenge for you, download the source code and try to make it so that you can use lambda expressions. But you'll have to change a few more references to rules and stuff like that.
Okay, one final question. Is it possible to use emojis as the operator code in the tokens file?
Is it possible to use emojis? I think Python supports Unicode really well, so I haven't tried it, but I'd say so. Just give it a try. Replace the pipe operator with, I don't know, a heart emoji, and give it a go.
All right. Thank you again for your talk.
Yes.
Thank you for answering the questions.